Okay, so welcome back. And so today we're going to start the topic of continuity, okay? So when we talk about functions, and we talk about them having a characteristic of being continuous, we often say that, hey, in order for a function to be continuous, we should be able to draw the graph of the function without lifting our pencil off the paper. And we would say that a graph that satisfies this idea, this characteristic, is continuous. Okay, so we're going to start with the idea of being continuous at a point, because we can have functions that are continuous everywhere, or we could have functions that are continuous on an interval, because there are functions that would have what we call a discontinuity, where there's a break in the graph, where you would have to actually lift your pencil up off the paper in order to continue to draw the graph of the function, or to sketch the graph of the function. So we would say that functions are continuous on an interval. Okay? So let's start with the idea of what it means to be continuous at a point, and we're going to take the intuitive approach, and then what we're going to do is we're going to add conditions and then come up with the definition of being continuous, or continuity at a point. So let's start with some examples. Okay, so the first one is we have this idea that in order to be continuous at a point, intuitively we know that we must be able to sketch that point without lifting our pencil off the paper. And so one of the things is like, for example, if we look at this graph here, right, and we want to look at the point A, well, at this point we have a hole in the graph, so this is not defined at A, it's undefined, right? So that leads us to consider that, hey, in order for a function to be continuous at a point, it would have to be defined at that point, right? Based on what we have here. Okay? So we would say that, so I will say that f of A must be defined. Okay, so f of A is defined. But as we can see from the second graph here, that's not enough. It's not enough to be defined at A, because here it is defined at A, right here. But this is still not continuous at A, because again, we still have to lift up our pencil and jump over here because of the break in the graph. So it's not enough just to have that condition. So now what we're going to do is we're going to add the condition that the limit, right? So let's add the condition that the limit as x approaches A of f of x equals exists. That's what I want to say. Exists, right? Because right now, here, the limit doesn't exist, right? Because again, if I approach A from the left or the right, I don't get the same value. So guess what? Okay, we want the limit to exist. So that's where this condition comes in. Okay, so now, with these two limits, right, or these two conditions now, we take care of that one, we've taken care of that, we avoid this one. Okay, so this is an example. This is not continuous at A. This is not continuous at A. So we came up with these two conditions. We want to make sure that the first one, f of A, is defined. Second, we want the limit as x approaches A of f of x to exist. Now, but then we have something like this. So this graph satisfies these two, but still it is not continuous at A because of the same idea I still have to lift my pencil off the paper, boom, and then jump back. So even though this graph satisfies these two conditions, it still is discontinuous at A. So now what do we have to do? We have to add one more condition. And the last condition, condition 3, is that the limit as x approaches A of f of x has to equal f of A. Okay? And so that brings us to the 3 conditions that we need in order to be continuous at a point. Okay? And so with these 3 conditions together is going to form the definition that we're going to, that I'm going to give you next time. Have a great day.